Okay, welcome to a new Geant4 tutorial on my YouTube channel Physics Matters. In the previous videos I explained already how you can create your first project, how you can insert certain features, for example detector geometry, and we have explained this with an example of a setup related to gamma spectroscopy. But until now we only used a particle gun to create our photons, our gammas. Now in this video I would like to go one step further and explain now in a little bit detail how you can insert your own radioactive source. So we could also model this radioactive source, of course, by our own. Then we get a more realistic setup. However, it's good to use as many features from Geant4 which are available as possible, so we can be sure that these features are tested and reliable. So the first thing which we have to do, we have to go to our include folder, and there we have already created a header file in one of the last videos, and it's called pmphysicslist.sh. And there we have to actually include two Geant4 header files in order to make sure that we can use these dedicated classes. So if we write here include G4 radioactive decay, then we can see that we have already some suggestions from Visual Studio Code regarding the header files that are included in Geant4. So what we actually need is one which is called G4 radioactive decay physics. So all physics lists usually end with the name physics. So we can use that one. And the second one that we want to include is G4 decay physics. So this is handling different decay models, mainly related to particle physics, but we also have to include it here for our radioactive decay. And then we go to our source file and to our physicslist.cc, and there we had in the past registered this electromagnetic physics, which is used for interactions of particles, electrically charged particles with matter. And the same we have to do now also for our radioactive decay. So we can write here a comment that we can call, for example, radioactive decay physics. And then we can write here register physics. And then we have to include here this class as new G4 radioactive decay physics. And the name is of course the same as the header file. And the second one is our decay physics file, and here we have to write register physics and then new G4 decay physics, and in both cases we have empty constructors, so we can just use empty parentheses here. And this is in principle everything which we have to do. Now our physics list is already completed and we can use now radioactive decay. But at the moment nothing will happen, so we have to of course modify our particle gun accordingly. So we go to our pmPrimaryGenerator.sh, and there we have to include a few more Geant4 header files. And actually it's only one, as I have just checked it. So it's G4 ion table.sh, and this is required in order to get access to the ions which are already predefined in Geant4. And then we can go in the next step directly to our pmPrimaryGenerator.cc, to our source file, and there we have to check what we have done at that time, and some things we have to delete. Because of course everything which is related to the particle type, where we have defined our gamma, this part we have to actually complete delete. The position and the momentum direction we can still include, but our energy of the nucleus should be 0 in the beginning, so we can also actually delete this one. And this particle definition we have also deleted, so we can also delete this part. And our particle definition we will now actually shift now to our generate primaries function. So of course we have to start here, and we will first define our particle type. So it should be an isotope, of course, and the only question is which one we use. So in this case I decided to use fluorine, so I can write here G4 int Z is equal to 9 and G4 int A is equal to 18. So this is a radioactive isotope of of fluorine, which is actually a beta plus source, but these positrons, they interact with the electrons in the atomic shell, and due to this reason you get two gammas, and these two gammas are emitted in opposite directions. Yeah, and they both have, of course, an energy which is equal to the rest mass of the positron and the electron, which is in this case 511 keV. But all that is handled by Geant4 automatically. We don't have to do anything. Yeah, then of course we have to define a few parameters more, and one is the charge, which is a double, yeah, because it's the elementary charge actually, but in this case our isotope should not be an ion. It should be a fully equipped atom, so to say. So we can just write here a 0 net charge, 0 E plus. If it has a charge, we can write here any other value, but in this case we can emit this, and E plus is the elementary charge, so to say. And G4 double, yeah, and this we have to call charge, of course. And here in the next we define the energy, which should be also 0, yeah, which means that our isotope does not have an initial kinetic energy. It rests at a certain place. Okay, and then now we can actually define our ion. So we can write here G4 particle definition ion, yeah, although it's not an ion because we said we have 0 charge, but it's still, according to the Geant4 definition, an ion. So we can write here G4 ion table. This is the header file that we have included already. And then get ion table. So we have to get an instance of that table. And then we can write here get ion. And here we then include our Z, which is the number of protons, and A, and energy. Yeah? And then in the next step we have to assign this to our particle gun. So we can write here F particle gun set particle definition that we have deleted already before. Now we have to add our ion here, and we also have to add our charge. So we can write here set particle charge, and then we can write here F particle gun set particle energy, and there we can include our energy, which is 0. Yeah, and in principle this is everything what we have to do. Maybe in order to make sure that it does not collide with our axis cross that we have created, we can actually shift it slightly in Z direction. Yeah, here we can also write -1 centimeter, and it should not have any momentum direction. Of course, we set an energy equal to 0, so it doesn't matter, but just for consistency, I want to also set this to 0. So now in principle, everything should be completed, and we can go to our build folder, and now we can compile our program. And if everything works well and we didn't make any mistake, it should run absolutely smoothly, which is the case. So now we can run our simulation file, and we can see here again our world volume with our scintillator, and here we see our axis cross, and then we can now run one event. Yeah, and this is very interesting. Yeah, so what we can see now here is our positron from that ion that moves inside the air. Yeah? And the reason for this behavior is that we don't have defined source material until now. So the beta particle is emitted without interacting with the electrons in the atom shell. And due to this reason, the positron is emitted and flies through the air until after some time we have a collision of this positron with an air atom. Yeah? And then we have here our annihilation, which then creates two gammas of 511 kiloelectron volt emitted in both directions. Yeah? But of course, we could use it now already, and it's also in minus 1 centimeter, yeah, as we can see here. We could use this already, but I would like to have a certain place from where our 2 gammas are emitted. So now we will define in the next step the material for the source in our detector construction. So we go to our PM detector construction header file, and we want to make it a sphere, a spherical volume. So we have to include a new one here, which is called G4sphere.hh. And this should be in principle everything for the time being. So now we can go to our PM detector construction CC file, our source file. And there we can now, before we create our source, we have to define the material. So we go here to our material definition part, so to say, and we have to add a few things here. So in this case, we want to define fluorine as a new material. So I can write a comment here, define fluorine 18. And first we have to use G4 isotope. Yeah, this class G4 isotope, and we call that F18 for fluorine 18, which is G4, which is new G4 isotope. And then we have to define a name. Let's call it maybe F18. And then we have to define here, we can see in this info box, we can see that first we have to define the number of protons again. So in this case, it would be 9. And the number of nucleons, complete number of nucleons, which would be in this case 18, neutrons and protons together. And then we have to define the molar mass, which is in this case, I just checked it, 18.000938 times gram divided by mole, approximately 18 gram per mole. And then in the next step, we have to, from this isotope, we have to define an element. So we can write here G4 element, and this we call maybe ELF18. And then we have to write new G4 element. And then first we have to give a name, which is fluorine 18, for example. Then we have to define a symbol. So in this case, we can write F18. And then in the next step, we have to type in the number of isotopes. And we have only 1. So we can just type in 1 here. And this, of course, we have to now assign. So we can write here ELF18 add isotope. And then we add our F18 here, our isotope that we have defined before. And then we don't have any other isotope, so we can write here 100%. And then, of course, in the last step, because our isotope and our element does not have any direct interaction in Geant4, in order to assign something to our logical volume, we have to create a material. So we have to write G4 material, and we call that maybe mat F18, new G4 material, and then F18 source, we can just give as a name. And then we have to define the density. So in this case, I checked it. It should be 1.51 gram per cubic centimeter. And then the last one is the so-called state. So we have to define if it's a solid, a liquid, gas, or whether it's undefined. In this case, it should be a solid. So we have to insert here 1. And then we have to write mat F18 add element, and then we have to add our element ELF18 100%, because we have 100% of the same element in our material. So there seems to be no error message until now. So what we can do now in the next step is really to define our source. So here we go below our fuzz world. And we define now our fluorine source. So let me also write it as a comment here. And then we can also define source radius, just to have it as a free parameter here and a variable. And then we can start with G4 sphere. So we want to have a spherical volume in this case. And then we can write here solid source is equal to new G4 sphere. And then this looks a little bit different to what we have defined before. Until now we used only G4 box, but now we will use G4 sphere. So we can check here how we can define that. And you can see here the third info box is giving us the right hint, so to say. The first one is the name as usual. So we can write here solid source. And then we can also make a hollow sphere, but we don't want this. We want a full sphere, so to say. So our minimum radius that we have to define here should be 0. And then our maximum radius should be our source radius. And then we have to define our minimum phi angle, our minimum azimuth angle, so to say. And this, of course, should be also 0. And our maximum azimuth angle should be 360 degree. And since Geant4 only knows how to handle radians, we have to multiply it with degree, which is, as you can see here, 0.017 and so on, in order to convert degree in radians. And then our minimum theta angle should be again 0.0, and our maximum theta angle should be 180 degree. So this is done. Now in the next step we can then define our G4 logical volume, and we can write here logic source, and this is again new G4 logical volume. And as we have done before, we have to first write here solid source, our solid volume. Then we have to write the material, which is mud F18. And then we have to give a name, which is in this case simply logic source. And now in the next step, then we have to create our physical volume. And we call that phys source. And this should be equal to G4V placement, similar to what we have done before. And there we have no rotation, so again we have to insert a 0. But we have a translation because we shifted our source to -1 centimeter in that direction. So the same we have to do here as well to make sure that our radioactive decay happens inside the volume. So we can write here -1 times centimeter. Then we have to assign our logical volume. So we have to write logic source. And then we have to give a name, phys source. Then we have to define our mother volume, logic world. And it should have, the copy number should be actually 0. And we want to check our overlaps, so we can write here check overlaps. Yeah, and in principle we could run it now and check it, but I would like to do something else, because I would also like to make it clearer visible. So we can add again some vis attributes, some visualization attributes, and this I could call maybe source vis add, which is equal to G4 vis attributes. And again we have to define a color here, so we can write G4 color, and I would like to give it 1.0 for red, 0.0 for blue, 1.0 for 0.0 for green, 1.0 for blue, and our alpha value should be 0.5 as usual. And then we can write here source with add, and we also want to make it solid, so we can write set force solid true. We don't want to have wireframe, we want to have a solid volume, but this is only of course for visualization, it has no other effect. And logic source, then we have to assign here set with attributes and then source with add. And now everything should be really completed. We can actually now test our program and compile it. It seems that we have not done anything wrong, so we can write here ./sim as usual. And now, if we are lucky, we can see our purple radioactive source here very nicely. And now what we can do, we can run it. So if we now press run beam on 1, we can actually see here that we have our 2 gammas directly coming out from that source. There is a third gamma, which is actually coming from another gamma decay that is happening. If I'm not wrong, it is the daughter nucleus which is decaying in this case. And yeah, so this is working very well. Yeah, we can also see that our gammas hit our scintillator. Yeah, this also works very well. What we could also do now, we can maybe create a few more. So we can write run beam on, maybe 100, and we can see now very nice, very nicely our gammas that are created, and some of them hit our scintillator and some of them not. So now what we can do after creating our simulation, we can go to our root file, in this case, for example, output 0.root, because it was run 0. And then we go to our EDEP histogram, and there we can see this nice histogram that we have also seen last time, but this time with a real model for nuclear decays. And then we can see here this background, but we can also zoom in a little bit and have a look at this part here. And there we can see 4 entries for photons with 511 keV. Yeah? So we are not using a particle gun this time. This is now a real radioactive decay. So many of the photons, gammas, just did not hit our scintillator, and those who hit the scintillator maybe just lost energy via Compton effect, and then they passed by, or they left the scintillator without doing any further interaction. So this is giving some background. But what we are really interested here is this peak at 511 keV. And yeah, you can play with this a little bit. You can create more events, and you can check how the distribution changes when you do that. Okay, and this is everything which I want to show actually, because in the next video then we will go one step further, and I will explain then there how we can create scintillation light in our scintillator. And then we will also attach another volume, PMT, where we can count the number of photons that we have in order to do further processing with that. Yeah. Until then, I hope you enjoyed the video. Thank you very much for your attention, and hopefully see you soon back for a new tutorial. Thank you very much for watching this video. If you like the content and want to see more of it, please like and subscribe. And in addition, any kind of support is always appreciated.